Good day, everyone. Today we are going to discuss another topic, and it is all about the vertical stresses in soil. So, we all know that soil is a multi phase system. It is a three-phase system, or sometimes it could also be a two-phase system. So, in a given volume of soil, the solid particles are distributed randomly with void spaces in between. The void spaces are continuous and are occupied by water and or air. To analyze problems such as compressibility of soils, bearing capacity of foundations, stability of embankments, and lateral pressure on earth structure, we need to know the nature of the distribution of stress along a given cross-section of the soil profile. In water, if we have pressure, in soil, we have what we call stresses. So to start with our lecture today, first we are to discuss stresses in saturated soil without seepage. So in stresses, we have what we call effective stresses. So this is the most important stress and it is also called the intergranular stress. And it is the stress carried by the soil solids at their points of contact. The sum of the vertical components of the forces developed at the points of contact of the solid particles per unit cross-sectional area of the soil mass. So effective stress is the stress due to the soil solids. And then we have what we call neutral stress or what we call pore water pressure. So pore water pressure or the neutral stress is a portion is carried by water in the continuous void spaces. We all know that. And then this portion acts with equal intensity in all direction. And this is the stress induced by water pressures. That means the neutral stress or the pore water pressure is the stress due to the water or the pressure due to water. And then we have what we call the total stress. So total stress is the sum of the effective and the neutral stress. But in discussing the stresses, the most important one is what we call the effective stresses or the intergranular stress because we are to determine the stress due to the soil solids. And then the principle of effective stress was first developed by Terzaghi in 1925 and 1936. So Skempton at 1960 extended the work of Terzaghi and proposed the relationship between total and effective stress. In summary, effective stress is approximately the force per unit area carried by the soil skeleton. The effective stress in a soil mass controls its volume change and strength. Increasing the effective stress induces soil to move into a denser state of packing. The effective stress principle is probably the most important concept in geotechnical engineering. The compressibility and shearing resistance of a soil depend to a greater extent on the effective stress. Thus, the concept of effective stress is significant in solving geotechnical engineering problems such as lateral earth pressure on retainer structures, retaining structures, the load bearing capacity and settlement of foundations, and the stability of earth slopes. The effective stress is defined as the sum of the vertical components of all intergranular contact forces over a unit cross-sectional area, as I have mentioned. And this definition is mostly true for granular soils. However, for fine-grained soils, the intergranular contact may not physically be there because the clay particles are surrounded by tightly held by water film. So, in order for us to understand more about stresses, this is a figure of soil with water. So, if you can see, this is soil submerged in water. or this could be water, I mean soil in rivers or streams. And below is the soil profile. So figure shows a column of saturated soil mass with no seepage of water in any direction. The total stress at the elevation of point A can be obtained from the saturated unit weight of the soil and the unit weight of water above it. The total stress at point A, so if you're to get the total stress, the total stress again is the sum of effective stress and the neutral stress. That means it is the stress due to soil and also the stress due to water. So the combination of the stress due to soil and due to water. So if we're to get the total stress at point A, this is point A. The total stress is equal to the height of the water multiplied by the unit weight of water. So the unit weight of this layer, and this is water. So, and then the height plus the height of this soil layer. So if you were to get the height of the soil layer from the water surface down to here, this will be h sub a minus h. That's why this will be h sub a minus h. And the unit weight of this soil. So the unit of weight of the soil is saturated unit weight. Because it is submerged in water, the groundwater table is above the soil layer. Automatically, the unit weight of the soil is saturated. To further discuss more of the stresses, let us look at this figure. So this is an example of a soil profile. It has surcharge load or additional load at the top. This is a first soil layer, second soil layer, and third soil layer. So if you can see, water table lies here. And at point A, if we are to get the total stress, it will be equal to the surcharge load, that is Q. It's already in kPa, that means it's already stress due to the surcharge load. And then we have to get the unit weight of this first soil layer, that is the moist unit weight. So, and then multiplied by the height from the ground surface. So the height from the ground surface is equal to h sub 4. That's why it's equal to h sub 4. Class, in this example, if you will see the unit weight is moist unit weight. If it is given in the problem that the soil is dry, so you will have to use dry unit weight because it's above the water table, so you would use dry unit weight if it's dry soil. But in this particular problem, it is said that this soil layer above the water table is moist, so you will use moist unit weight at this point. So if you get the neutral stress at point A, the neutral stress is equal to 0. There would be no neutral stress above the groundwater table. It will always be just below the water table. If it's it has even if it's saturated here and the groundwater table is located here, there will be no neutral stress. Take note that the neutral stress is due to the water table here. So if you're going to get the neutral stress above the water table, neutral stress is equal to 0. And if you're going to get the effective stress, we all know that effective stress is equal to the total stress minus neutral stress because the total stress is equal to effective stress plus neutral stress. If we were to get the effective stress because it's always the required one, not the total stress, we're just going to subtract the neutral stress from the total stress. So effective stress here is equal to Q plus unit weight, moist unit weight H sub 4 minus 0. That's why this will just be equal to Q plus moist unit weight H sub 4. So at point B, if we're to get the total stress, this is equal to Q due to the stress due to the additional load or surcharge load. And then plus, where is point B located? This is here. So you have to get the stress here first and then get the stress here. So this will be equal to the moist unit weight multiplied by the height of this soil layer. What is the height of the soil layer? It's equal to H sub 1. That's why this will be unit weight, moist unit weight plus H sub 1. So, hanggang dito pa lang yung stress ha. Tapos, para makuha natin yung stress hanggang point B, we have to get the unit weight of the soil. At this point, the unit weight of the soil is already saturated because it is below the water table. So we are to use the saturated unit weight sub 1, that is equal to that. And then the height from this groundwater down to the point B, and that is equal to H sub 5. And then, if we are to get the neutral stress, again, ang neutral stress, if we are to analyze, ang neutral stress nagsisimula lang sa groundwater table. So, if we get the neutral stress due to the groundwater table at point B, the neutral stress is equal to, what is the unit weight of water? That's 9.81. That's why unit weight of water is here. And then the height from the groundwater table is H sub 5. That's why this is H sub 5. And then if we get the effective stress is equal to the total stress minus neutral stress. So the total stress is equal to Q plus moist unit weight H sub 1 plus saturated unit weight sub 1 H sub 5 minus the neutral stress is equal to unit weight of water multiplied by H sub 5. To further analyze, let us look at these terms, at the last two terms of the equation. So if you look at the last two terms of the equation, H sub 5 is common. So this will be equal to Q plus moist unit weight H sub 1 plus quantity saturated unit weight sub 1 minus unit weight of water multiplied by H sub 5. And then if we look at this one, we all know that the saturated unit weight minus the unit weight of water is equal to the buoyant unit weight. That's why this is equal to buoyant unit weight. It has buoyant unit weight in here. So, therefore, the effective stress at point B is equal to Q plus moist unit weight H sub 1 plus buoyant unit weight sub 1 H sub 5. Now, if we're going to analyze the stresses at point C, the total stress at point C is equal to the surcharge load Q plus moist unit weight of this soil layer multiplied by H sub 1. And then plus the saturated unit weight of this soil layer multiplied by H sub 2. So this is H sub 2. Disregard H sub 2 in here. What I'm referring to as H sub 2 is the H sub 2 from the groundwater table down to this layer That's why it's H sub 2 in here. So there are two H sub 2 in the figure. I missed uh, that. And then down to this layer at point C, we have to get the saturated unit weight of this layer. That's why it's saturated unit weight sub 2 multiplied by the height. Hanggang dito pa lang kasi yung nakukuha natin. So, we have to get the uh, height from this layer down to this point in order for us to get the total stress. So this is H sub 3. That's why the total stress is this. And then if we get the neutral stress is the neutral stress from this layer or this point down to this point. So the neutral stress is equal to the unit weight of water, H sub 2, this is H sub 2 again, plus the unit weight of water down to this point, H sub 3. In order for us to get the effective stress, again at point C, we have to get the difference between the total stress and the neutral stress again. So this is the neutral stress subtract by the, I'm sorry, this is the total stress subtract by the neutral stress. So if you're going to analyze the equation, again, there are common terms like H sub 2 and H sub 3. Therefore, if we combine the saturated unit weight minus the unit weight of water here, H, and then multiply it by H sub 2, and then saturated unit weight sub 2 minus unit weight of water multiplied by H sub 3, you'll get again or will get the buoyant unit weight sub 1 and the buoyant unit weight sub 2. So the buoyant unit weight of this soil layer and the buoyant unit weight of this soil layer. So therefore, the effective stress at point C is equal to Q plus moist unit weight H sub 1 plus buoyant unit weight sub 1 H sub 2, or the buoyant unit weight of this soil layer plus buoyant unit weight sub 2 multiplied by H sub 3. In order for us to understand more, let us look at this sample problem. So in this sample problem, there are 3 points in here, and this is a dry sand, first layer. There is a groundwater table, and definitely because this is below the groundwater table, this is already saturated layer. And then we are to calculate the total stress for water pressure or the neutral stress and effective stress at points A, B, and C. So let us first solve the stresses at point A. So if we're going to analyze, at point A, walang lupa sa taas ng point A. Definitely, dahil wala namang lupa at walang tubig sa taas ng point A, total stress will be equal to 0. And then, also, the neutral stress will be equal to 0 because there is no water above that point. So neutral stress is equal to 0. And lastly, if we get the effective stress, it's also equal to 0 because effective stress is equal to total stress minus neutral stress. That's why it's equal to 0. Let us look at point B. If you're to get the stress at point B, the total stress is equal to the dry unit weight of this soil multiplied by the height. So the height from the groundwater the ground surface is 6 meters down to this layer. That's why dry unit weight times 6, it's equal to, given dry unit weight of sand, it's equal to 16.5 times 6. Therefore, it is equal to 99 kilonewton per square meters, or 99 kPa. And then, if you look at the point B, the neutral stress at point B, as I have mentioned, neutral stress is due to water. So we have to get the unit weight of water multiplied by the height from the groundwater table of the point where we are to get the neutral stress in order for us to get the neutral stress. So in this point, at point B, ang height from the groundwater table ng point B is 0. So, if we're to get the neutral stress at point B, it is equal to 0 because wala pa namang height from the groundwater table yung ating point B. That's why the neutral stress is equal to 0 pa. And then, in order for us to get the total stress at point B, the effective stress at point B, this will be equal to the total stress minus the neutral stress. It will also be equal to the total stress because neutral stress is equal to 0 as 99 kilonewton per square meters, or kPa. And then, if we get the stress at point C, it is equal to the unit weight of this soil multiplied by 6, and then unit weight of this soil multiplied by 13. This is the layer of the soil. So this is why it's equal to dry unit weight times 6 plus saturated unit weight times 13. Again, why is it that it's saturated unit weight and why is it that it's dry unit weight? It's given already in the problem that it is dry sand. Also, why is it that it's saturated unit weight again? Because it is under the groundwater table. Automatically, it will be fully saturated. That's why the unit weight is saturated. So, the total unit weight is equal to 16.5 times 6 plus 19.25 times 13. So, the total unit weight is therefore equal to 349.25 kilonewton per square meter, or kPa. And then, if we are to get the neutral stress or the pore water pressure, it will be equal to the unit weight of water multiplied by the height from the groundwater table of the point. So the height from the groundwater table of point C is equal to 13. So from here, this is the groundwater table, down to point C, that is 13 meters. That's why this will be equal to the unit weight of water multiplied by 13. And we all know that the unit weight of water is equal to 9.81. You have to multiply it by 13. And therefore, the neutral stress is equal to 127.53 kPa, or kilonewton per square meters. And then, in order for us to get the effective stress, it's equal to the total stress minus neutral stress. It's equal to 349.25 minus 127.53. So the effective unit weight is effective stress is equal to 221.72 kPa, or kilonewton per square meters.